Hello everyone. Today we are going to start with the chapter 1 of the standard 10 forces. Regarding forces, basic details, basic effects, basic idea what exactly the force is, all such things has been discussed in the lower classes 6th, 7th, 8th, even in 9th. Now getting into little bit of detail, right, about the rotational and translational motion. We'll discuss the force but in reference to the force which causes translational motion and that causes the rotational motion. Regarding translational motion, a quite bigger explanation, a deeper discussion is present in the 9th standard. In the 10th standard, specifically we'll talk about the forces creating a rotational motion. So starting with the chapter 1, forces, translational and rotational motion. The first terminology we have is translational motion. Before we begin with this chapter, I want you to be very clear about the teaching and learning. One thing is understanding the concept, the terminologies, physical quantities, right? So what exactly they are, or what effect they give, or what is the final outcome of that discussion. So one is the conceptual understanding and other thing is presenting in the paper. You may understand a particular topic through so many examples, but you cannot write only the examples in order to explain a topic. When the question is asked, define, right? So first thing what a checking person, a checker expect is the definition or some precise explanation. So as I teach the topics, I'll give you a brief definition or a brief explanation as a part of the answer, and then examples you may write on your own as per your preference. Some of the examples I have shown here, you can use them, right? So starting with first topic we have is translational motion. So to be precise, what is a translational motion? So translational motion, it is a motion in a straight line. Whenever body moves in a straight line, we say the body is describing a translational motion. So translational motion, motion in a straight path, motion in a straight path, right, is called as translational motion. So you may think of a car on the road, right? It travels into the straight path. Don't get into very much detail that while moving from one city to other city it takes a turns, right, because of the speed breakers, because of the any other obstacle, the car may go slight up and down. So don't get into so much of detail. Just for a simple understanding, for a shorter distance car travels in a straight line. For a short distance car travels in a straight line, it takes a translational motion. The best example to understand translational motion is a fruit falling from a tree, right? Fruit, when it gets detached, it covers a very considerable amount of height, right? It's not traveling a very long distance. Even if you throw something from the 4th floor, its path may slightly change because of the wind, right? But when the fruit is falling from the tree, the height is much comfortable enough so as to ignore the effects of air or any other sources of friction. So fruit falling from a tree, it's a best example of a translational motion. It takes a very straight path. The perfect example which you can ever give for a translational motion is a fruit falling from a tree. Soccer ball, when it is kicked, right, it moves into the straight path. However, it takes slight turn, it may take a flight, but the suffix for a short path need to be added when we take such examples. So soccer ball for a shorter path moves in a straight line, car for a shorter path moves in a straight line or undergoes a translational motion, train for a shorter distance, maybe 10 meters, maybe 5 meters, undergo a translational motion. So translational motion, it is a motion in a straight path. Next we have rotational motion. So rotational motion, it is a motion along a fixed axis. Whenever the axis is present, you apply force anyhow. There is only one outcome, that is the object will rotate. If the object have a axis, then for sure there is only one outcome, that is rotation. The best example is a fan. If you take a fan, right, see, this is the axis along which the fan is going to take a turn. So motion along this axis, the motor present in the middle of the fan, right, it provides the force, and that force along this axis produce a rotational motion. Top along this axis, right, it produce a rotational motion. So motion along a axis, there must be a axis, right? The door, do door possess a rotational motion? Yes, the door has a hinging at one of the end, right? Let's say if you draw a door, it has a hinging, one this side hinges are present. So because of these hinges, it is nothing but the axis, hence door also takes a rotational motion, not a complete rotation but a part of rotation. You can call it as a rotational motion. So rotational motion, it is a motion along a axis, fixed axis, right? Then comes the combination of translational and rotational motion. This, when we say combination of two motion, the discussion becomes quite complex one, because whatever motion you think of is involved with multiple motions. Let's say car, apart from translational motion, the car also takes a turn. Car may also slightly bump above because of the speed breaker, so it becomes a motion in a plane, right? It becomes a directional motion. The wheels of a car undergoes rotational motion, so car itself is in the translational motion, wheels are in rotational motion. The piston within the engine of a car undergoes oscillatory motion. The piston vibrates and the energy of its vibration is transferred to the wheels. So when you consider a object at a very into a very detail, right, it is made up of multiple motions. So translational and rotational motion, as I gave you example, a cycle rider, he is in the translational motion as well as the wheels are undergoing a rotational motion, right? Soccer ball, or even you may say a cricket ball, right, it has a translational motion as well as it is undergoing a rotation along some imaginary axis. The axis can't be seen here, but it can be imagined to be passing through the center of this ball. So translational and rotational motion. Next we have rigid body, right? To discuss the rotational motion into detail, right, we apply the concept of rotational motion onto the rigid bodies. Regarding non-rigid bodies, the discussions are quite complex. Whatever discussions we do about a rotational motion in 10th standard are on the rigid bodies, not on the non-rigid bodies. So what are a rigid body? So rigid body, it is a body which does not get deformed even on application of deforming forces. It's called as a rigid body, right? You apply a force. See, I'm applying a force, but still its dimension, it's not changing, its shape is not changing, right? Which does not get deformed. Deformed, it means no change in shape, size, right? Or you may say dimension is a better word as compared to shape, size, length. If you replace those words with a dimension, it becomes more precise, more perfect. So rigid body, it does not get deformed, its dimension do not change even on application of a force. This pen, I am applying a force, but its dimension is not changing, its shape is not changing. So is it a rigid body? Think a bit and tell me, is a pen a rigid body? Right, I am applying a force, its dimension is not changing, its shape is not changing. So is it a rigid body? Yes, the pen is a rigid body, and if you get into details, there is no body which is perfectly rigid, right? Instead of me, let's say a machine applies the force, for sure it will change its shape, it will break down, right? For a small amount of force, even the screen is non-breakable. But let's say if I apply force with machine, the screen will break for sure. Even a metallic pipe, it may not be possible to bend it with your hands, but with the machines you can easily change its shape. So when we say a rigid body, it does not mean that the dimensions can't be changed forever or by anything else. It means that by a considerable amount of mechanical force which we humans can produce, its dimension should not get changed. By the mechanical force which we humans produce, by that force the dimension should not change. Then we say the body is rigid body, right? You can see a brick, with your hands you can't break, rigid body. Iron rods, right? With your hands its shape may change a slight, but it does not get broken up, or it completely do not change up, as long as the rod is short one, right? So again a rigid body. Metallic tubes or pipes, wooden log, its shape not does not change, right? Even if you sit on it, even if you try to bend it, its shape is not going to change. So a rigid body. Then next we have some terminologies very much useful in study of rotational motion. Point of application of the force. Point of application of force means it is a point at which the force is applied, the point exactly where the contact take place. That point we call it as a point of application of force. You can see here, this is exactly the point where the force is acting. See here, this is exactly the point at where the force is acting. So point of application of force, it is defined as a point, you can say a imaginary point at which force is applied. So point of application of force. So wherever your hands touch, it is a point of application of force. What is the use of point of application of force? All these terms, they help us to understand rotational motion into details. These terminologies are very much used when you study rotational motion. Then next we have line of action of force. So how do we define it? From the point of application of force, here we'll add it as imaginary line drawn from point of application of force in the direction of force. So see here, I have applied the force from the point of application of force, right? I am drawing one imaginary line. So this imaginary line is called as point of application of the force. What is the meaning of line of action of force? It means that along this line, wherever you apply the force, same effect is going to take place, right? Let's say this box, whether I push it from here or somewhere the imaginary line passing through its center, or if I push it through some other point, the box is going to advance in a same forward direction. So line of action of force, it is nothing but imaginary line drawn in the direction of the point of application of the force. Imaginary line drawn from the point of application of force and in the direction of the force. This was the point of application, and the direction was this. So in this direction I have drawn one imaginary line. This imaginary line we call it as a line of action of force. Then next we have principle of transmissibility of force. What does the principle of transmissibility of force says? It says that the point of application of force can be transmitted anywhere along the line of action of force. So along the line of action of force you can shift the point of application of force, right? You applied the force here, but this point can be also shifted here, can also be shifted here, can also be shifted here. It's going to produce same effect. So shifting the point of application of force anywhere along the line of action of force, by this shifting we just do some adjustment so that the effort which we are going to apply becomes less. What is the use in shifting the point of application of force? Right? In shifting the point of application of force or adjusting the point of application of force anywhere along this line of action of force will reduce our efforts. So principle of transmissibility, it says that the point of application of force can be transmitted anywhere along the line of action of force. Then next we have movement of force. Now we exactly come into the detail or into the discussion of the rotational motion. So the first physical quantity that we have in the rotational motion is a movement of force or torque, right? How do we define a movement of force? So movement of force, it is defined as a turning effect of force along a fixed axis. So first thing is we need a fixed axis, and along the fixed axis wherever you apply the force, along the fixed axis wherever you apply the force, it's for sure going to create a turning effect, right? And that turning effect of force, or we call it as a torque. Instead of speaking the full words that the force has produced a turning effect, instead we say the torque is acting, right? Let's say this screen, right? If I rigidly connect it from this end, if I rigidly hold at this end, and then if I apply force anywhere, it's going to rotate, right? You can see here this spanner, it is rigidly held at this axis. Now you apply the force over here or over here, it's going to take a turning effect. The turning effect may be full rotational or may be a little bit one, right? So turning effect of the force along the fixed axis, we call it as a movement of force. This movement of force, it depends on movement of force or torque. Torque is denoted by the Greek alphabet tau. Tau is the Greek alphabet which denotes the torque. So torque depends upon, first thing is perpendicular distance. Perpendicular distance means distance from the axis of rotation. This is the axis of rotation, and from here what is the distance where the force is applied. And second thing, it depends upon magnitude of force. So these are the two factors which, if you control, the movement of force may be large or may be small, right? If you want a larger movement of force, let's say if you want to open the nut of truck, so nuts of truck are too tight, they can't be opened just with your mechanical effort. So what does the truck drivers or truck servicemen do? Instead of the smaller handle, they use a much larger handle. much larger handle, and then they apply the force. Now see here, the perpendicular distance is more, ultimately the torque will be more. Torque is directly proportional to the perpendicular distance, and it's also directly proportional to the magnitude of force. Now for force we have a limitation, right? Human arms, they can produce only a limited force. Let's say human arms can produce hardly 150, 200 or maybe 300 newtons of force, right? But the turning effect here required here maybe 3000, right? So with the help of force of 300 newtons and maintaining this distance as 10 meters, you can produce a torque of 3000 newton meter, right? So by increasing the perpendicular distance, turning effect can be increased. By increasing the force also, the turning effect can be increased. Door is an example where the torque comes into action, right? Door is hinged at one end. Let's say this is a door, it is hinged at one end. So let's say if you try to apply the force over here, just note that the perpendicular distance is very small, hence it may be difficult or the door may not open. But if you apply the force over here, just note the perpendicular distance is large, hence the door will open up easily. So for torque, the distance should be large, ultimately the torque will be more. Factors affecting the moment of force, right? Perpendicular distance and magnitude of the force. This is the perpendicular distance, right, from the fulcrum. So this is the perpendicular distance. Now this lady with such a long perpendicular distance can easily lift a very heavy load. If there was no such arrangement, this arrangement we call it as a lever. Simple rod, right, and fulcrum we try to open it, opening a soda bottle, right? So such a lever, if it was not there, it's almost impossible for this lady to lift up this stone. So such an arrangement, right, using a physics, the perpendicular distance, right, and here is the downward direction, she applies the force. So force and this perpendicular distance give rise to a turning effect, and this turning effect is given by perpendicular distance into force. This is the formula for the torque. How much torque is experienced by this stone? Distance multiplied by force, right? If the torque is enough, the stone will get lifted up into the air. Next we have clockwise and anti-clockwise movements. So fulcrum means a point through which rotations are possible. Fixed point, you may also say a hinge. So along this fulcrum or along this point of pivot, right, pivot, fulcrum, hinging, these are the points through which rotation is possible. So from this pivot, right, you can rotate the left side in a anti-clockwise direction or the right side into a clockwise direction, right? So if you apply a force in the downward direction on the right hand side, the arrangement, the seesaw is going to rotate in a clockwise direction, and if you apply the force on the left hand side in a downward direction, the seesaw is going to rotate in a right hand side. It's going to rotate in a anti-clockwise direction. The anti-clockwise movements, they are taken as positive, and clockwise movements, they are taken as negative. Please remember, in numericals it's of lots of importance. Clockwise movements are taken as negative, anti-clockwise movements are taken as positive. How to calculate movement or how to calculate the torque acting? Once again, the force we have here F, right, and then we have the distance, and then we have this distance. So force into distance will give you the turning effect tau, or will give you the movement of force. Both the words are used, and here also the same thing. You have a force over here, and this will be the perpendicular distance. We'll get the torque. Anti-clockwise movement, right, is positive. Clockwise movement is negative. You can see here anti-clockwise movement. You can calculate both the sides movement. Here anti-clockwise movement will be the force, the buoy is of 450 newtons, and the distance from the fulcrum is 1 meter. So anti-clockwise movement is 450 Newton meter. And for the girl, she is producing clockwise movement. It is 300 into 1.5, that is once again 450 Newton meter. So you can see both of them are producing same torque. Ultimately the seesaw will remain balanced. In case if any other person comes and sits over here, the condition of equilibrium will get disturbed. Anti-clockwise movement will dominate, and ultimately the seesaw will bend from the left hand side. Next we have units of moment of force, units of torque, right? So from the formula itself we can get the units. We have absolute units and gravitational units. Absolute units does not depend upon the gravity of planet, whereas gravitational units, they depend upon the gravity of planet. So absolute units of the torque, force is measured in Newton and distance is measured in meter. So we have Newton meter as a SI absolute unit, Dian centimeter as a CGS absolute unit, right? The force will be in the dian and distance will be in the centimeter. SI gravitational unit is kgf meter, and CGS gravitational unit is gram force centimeter. Units of the torque. Torque is measured in Newton meter or Dian centimeter. Very rarely these gravitational units are used.